Hello, my lovely students. So we have section 3.3, which is on inverse functions. So a good chunk of this should actually be a review from 1073, but we do have some added terminology. So we have these two fancy math ideas. We've talked about a function being 1-to-1 means for each x, there is only one y. So it passes the horizontal line test. There's also this idea of being onto. So let D be a subset of the real numbers R. Let f be a function defined from D into R, and let it be a function. We say that f is onto if for any y in R, there's at least one x in D, the domain set, such that f of x equals y. Informally, the function f is onto if its range covers all of R. So the wording here is a little bit weird, but basically I can have a graph that may not cover like all of the x values, but it could hit all of the y values. We would call that onto. Most of the time, we don't talk about whether a graph is onto, but when we get to trig functions, we get these kind of weird breaks in the graph, and so this idea can come up. Now, I do want to remind you, so since we're talking about inverses, functions that are not 1-to-1 do not have inverses that are functions. They do have an inverse graph, and it might be a kind of piecewise setup that we could do for inverses. But what we will see is when a function is not 1-to-1, if we restrict the domain, then we can have a function on that restriction that is an inverse. So if a function is not onto, then there's a y value that don't have an x value mapping to them. What that means is for the inverse is that we would need to restrict the domain of the inverse to accommodate these graphs in the range of the original function. Maybe. All right. So inverse function we have added now for any 1-to-1 and onto function, f of x equals y, a function f inverse of x, and that's how it's read, is an inverse function of f if f inverse of y equals x. So if f takes x and maps it to y, f inverse has to take y and map back to x. So we can also write it as a nested function, f inverse of f of x equals x, and it also follows f of f inverse of x equals x for all x in the domain of f inverse. So I highlighted that because when we get to our trig functions, the domain is going to be critically important, and the range. So our trig function inverses are only going to work for particular things. Now, another big thing, this inverse notation is not the same as 1 over. I know we use that -1 power, and like this dichotomy exists throughout all of math. So if you see f inverse where that -1 is on the f, assume it's talking about an inverse. If a math problem means 1 over f of x, they have to write it 1 over f of x. We reserve this notation for inverses. So a lot of times, now if you see x to the -1, that's a little bit different. But if you see it on any other thing, generally it means inverse. All right. So now we've just got a little bit of practice and we're going to have finding the inverse of a function. So if for a particular one-to-one function, f of 2 equals 4 and f of 5 equals 12, what are the corresponding input and output values for the inverse function? So if 2 maps to 4 in the original function, then the inverse has to take 4 and map it back to 2. So then 4 is the input and 2 is the output for the inverse. Likewise with our other pair, f inverse has to take 12 and go back to 5. Now, one of the ways you can see this is if I take the original statement, f of 2 equals 4. Let me move that over a little. I'm going to apply the inverse function to both sides. So the same way in an equation, I can add something to both sides, subtract something from both sides, divide by something on both sides, or square root both sides. We can apply the inverse to both sides. Now the catch is that sometimes the inverse, applying it like this, we might have to account for weird stuff happening. But just in the very general sense, f inverse of f undo each other the same way square root and square do. So then we would just have 2 equals f inverse of 4, which is what I wrote over here in pink originally, just reversed across the equal sign. So this idea of applying an inverse function to both sides is what we're going to be using a bunch. But we're going to have to remember, just like with square roots, the whole plus or minus thing, with trig functions, it'll be a different thing we have to remember, which is a restriction on what we can apply it to and what answers we can expect out. So given that h inverse of 6 equals 2, what are the corresponding input and output values of the original function? Okay, so if h inverse of 6 is 2, h inverse of 6 equals 2, then if I apply h to both sides, the entire sides, on the left, that's going to cancel out. And on the right, we have this. So now 2 is the input and 6 is the output. When we're talking about h, when we're talking about h inverse, 6 was the input and 2 was the output. So when we talk about this whole input-output thing, it depends on the function we're talking about when we talk about it. All right, so testing inverse relationships algebraically. So back in 1073, this is where we wanted you guys to show if something was an inverse function of a particular function. And you would do this by putting one inside the other. So this is the turducken of mathematics, for those of you who didn't hear my bad joke. So we are going to check, can I handwrite? When I put G inside F, do I get X? That's true if F and G are inverses. Now, technically, you're then supposed to check G of F of X, but for the stuff that we're going to be playing around with, if it works one way, it's going to work the other way. Usually the flipping it around, all you run into then is you're really checking like domain and range restrictions. But in later math classes, like you have to check it both ways because then functions are doing weird, crazy math things because you're in the land of pure math. All right, so f of x is 1 over x plus 2. So f of thing is 1 over thing plus 2. And now let's take our thing, which is 1 over x is a little fraction, minus 2. 1 over x is a little fraction, minus 2. Okay. So I have my f, I've put my g inside. So again, I want you to focus on functions are processes. They're things we do, a set of dance steps, if you will. The inverse undoes the set of dance steps. All right, so our original function, we took our input, added 2, and then took the reciprocal. So now our g of x says, okay, we'll take the reciprocal and then subtract 2. So it's doing the steps backwards. So if I have 1 over x minus 2, and then I'm supposed to add 2, well, that minus 2 and plus 2 undo each other. So now I have 1 over x. And I'm going to put extra parentheses around the bottom just to be clear, like where the big fraction is versus the small fraction. This is the same as 1 divided by 1 over x, like this. And then our fraction math comes into play. So this becomes 1 times x over 1, which is x, which is what we wanted to show. So we've done the thing, then we say, therefore, f and g are inverses. All right. So down here, slightly different function. Here I've got x cubed minus 4, and g of x is the cube root of x plus 4. But let me do example 3 first. So it also has a cube, and then they wrote 1/3 of x. So since that one doesn't have that extra 4 in there, let's play with that, see if it works, and then we can come back. All right, so we're going to test these guys. So f of thing is thing cubed. G is 1/3 times thing. So 1/3 times thing, all that cubed. Well, this is not going the way I'd want if I was wanting an inverse, because now we're going to cube 1/3 and those don't cancel out. 1/3 cubed is an even smaller fraction, and then we still have x cubed. So this would be 1/27 of x cubed. So these are not inverses. So it's not just about like putting one inside the other and saying equals x. Like when we ask you to test, there's a chance it won't work. Like you guys need to be able to see what it looks like when it works and when it doesn't work. And the easiest way to get used to that is to actually do the process. I know it's tedious, but it is worthwhile. So go ahead, take a moment, try this one out, pause, and then come back and see how I do it and see if you match. It's one of the better ways to use these videos. So now I'm going to go. F of thing is thing cubed minus 4. Our thing is g, which is this huge cube root of x plus 4. Huge cube root of x plus 4. So your brain should be like, all right, well, I am seeing what looks like inverse things. All right, so here we have the cube root and the cube as the outermost things. Those guys set up in that situation cancel each other out, they undo each other. So we end up with just x plus 4. And then we still have the -4 from f. And now +4 and -4 undo each other. So we are left with x. So yes, these are inverses. So for power functions, like that 1/3 comes into play, but what it actually is it'd be x raised to the 1/3 power, not 1/3 times x. So the cube root, another way of writing that is as a fraction power. So that's what this example was really like starting to hint towards, is thinking about that. All right, so our domain and range of inverse functions. The outputs of f are the inputs of f inverse. So the range of f is also the domain of f inverse, and likewise for the reverse. So when I have domain of f, I have the range of the inverse. When I have the range of f, I have the domain of f inverse. So it's like f goes one way, f inverse goes back. So those of you who have asked in the past, how do we find the range of a function? Like, we spend all this time figuring out how to find the domain and domain restrictions. How do we find the range? We're going to see in a sec how to find the inverse algebraically, and then you just find the domain of the inverse, and that'll be the range. And that is like legit the only way I've seen to algebraically determine the range of a function is to find its inverse and figure out the domain of the inverse and know that it's the same as the range of the function. I know it's kind of silly. All right, so here, if the domain of f is this and the range is that, what's the domain and range of the inverse? So domain of f inverse will be -infinity to -2. The range of f inverse will be 1 to infinity. So we swap x's and y's. I've been talking for a while, so I'm going to cut that and then record another.